Good morning, January the 30th, 2023. Let's look at problem 4. Actually, I thought the proof was really complicated in itself, easy to understand following the proof in the book, but that I should be able to make a proof doing something else appeared far-fetched. Well, as usual, one must look at the examples, and the Gaussian character modulo 5 looks like this, and I made this because I wanted to check that it was primitive. And if we take 2 plus I, the ideal generated by 2 plus I, then this gives naught, this gives unity, this gives -1, so it's not trivial. So it seems to be primitive, but will I be able to prove it? Well, I thought the natural way to do was what they did in the book, and that seemed quite natural. All right, then we take the prime being equivalent to 3 modulo 4, where then it's obviously primitive because 3 and 7 are Gaussian primes. So let's compute the character here, and then I realized that, I knew that in advance, of course, that psi only depends on the column, so we had to add up the columns. The sum gives -1, +1, -1, so nothing special here. Then I made the example modulo 7, and I only filled out the first quadrant, because it's mirror symmetric, and of course it's also mirror symmetric in the diagonals and rotational symmetric, so there are a lot of symmetries. So this is equal to this, etc. All right, adding the columns again. We'll do that down here. So here we have 2 minuses and 1 plus, that gives 1 -1, so -2. So altogether the sums in all of these is -1. And the sum on the imaginary axis is 6. And of course this adds up to naught, as it must. And then I realized if we could prove this, then it was easy, because then g of psi would be -1 times the sum of psi of x plus 6 plus 1. So this is p -1, of course. But then I took a -1 here, so we have to add 1, so it's just p times psi of naught. The sum here vanishes, and psi of naught equals unity, so it just gives p. Oh, if I could prove this, then we're finished. Now let's check if it holds on the other guy, which we've got here. Actually, I shouldn't have taken this row or this column. It's just these that matter. And we see the sum in each column equals -1, and in the on the imaginary axis it equals p minus 1. So that's my program. I want to prove that the sum of these columns give -1. I have no idea how to do that at the moment, but I believe it's the only way we can add up to a sum giving p, so that must be it. Think a little about it, and then we'll start recording again. I just checked my theory on Mabel with various primes. Just make it slightly bigger for you. Now if we take 7, then we compute the first quadrant with imaginary part equal to 1, 2, and 3. And the sum of that, each column in that quadrant, gives -1. So the whole quadrant, the top is -1, the bottom is -1, and the real axis is +1. So I just checked it with higher primes, and the ones I tried, there were not many, it turns out to be the same. We begin to believe it. Then I got an idea. This is the Legendre symbol. And modulo p, we know that it's equivalent to p minus 1/2. Modulo p. When I thought that, I immediately thought about applying the binomial theorem. A squared to this give a to, I'll just put this on. A squared to this power gives a to p minus first. And b to n minus I, p to minus first. And we know that a to p minus first is equivalent to unity. Now we need to be precise, which guys do we sum over? And we sum, say, from I equals 0 to p minus 1 halves. So we go up half the column and the real axis. And the sum of I think this gives 2 to, and then it just escapes me. So let's make an example. N equals 1, 2, 3, 2, that's 1, 1, 3, that's 1, 3, 6, 4, 1, 4, 6, 4, 1. So now what's that? It's 3, 1. Sorry. 2, 16, 8. I actually thought the sum was 2 to the nth. It's 2 to the fourth, 2 to the third. It's of course this, and here it's 1, 1. Right. So it's 2 for 2 to the nth. So it's 2 to p minus 1 halves. And then we need to know what that is modulo p. I actually thought that depended on p. Go from 0 to p minus 1. Well, we have made progress. I need to think a little about this. I just looked at it, and this was a stupid mistake, because we have to take distinct powers here. It's a squared to ith and b squared to n minus ith. So this doesn't work. Bad idea. I got another one. We have to compute this symbol, and a and b, let's assume, now if a is naught, then it gives unity. So let's assume a is distinct from naught. Then b divided by a makes sense in fp. The first guy, a squared, is a square. So it's equal to 1 plus t squared over p. And t squared, if we take the whole column, it runs through all of the squares. But it does so for whatever a is. It must run through all the squares. And that means that this sum is independent of a. Sorry about that, just had to take the phone. Now, what was it? Oh yeah, that means that this value will give the same whatever a is, as long as it's distinct from naught. And that means the sum of all the columns give the same, and that must add up together with this to unity. So this one, we know there's p minus 1 giving unity, and there are p minus 1 columns that all must give the same, that must be minus 1. So that constitutes a very simple proof, which I didn't expect to find.